Hey guys, so welcome back to another video. I'm gonna look through our lecture today on series and sequences and a bunch more theorems that we were doing today. And so we're gonna start off with this theorem that says if the sum to infinity of a series converges, then that means that the infinity of the term at infinity must be equal to zero. And that kind of makes sense, right? Because if the sum ends up to have a limit, it ends up a finite number, then the sequence can't be increasing exponentially, right? It has to kind of die down until the term at infinity reaches zero. And so that kind of makes sense. If a sum to infinity converges, then that must mean that the final term in the sequence must be equal to zero. And there's proofs here, but that's kind of a logical thing to think about. And then there's another contrapositive of that theorem itself, which says, and contrapositive just means if P then Q, then the contrapositive would be like, I believe it would, this is the wrong, maybe it's the, if not Q, then not P. But in general, the contrapositive of that says that if the limit of the sequence, which means the final term, the term at infinity, is not equal to zero, then the sum to infinity is divergent. And again, that makes sense, right? It's literally just stating this. It's the other way to state this is that if the term at infinity is not equal to zero, that means that the function must be divergent, because if the term at infinity is equal to, like, let's say 100, then that means the one before must be equal to 99 and all those kind of things, and it keeps adding up and adding up and adding up, and so that means that it will become infinity. So if the term is not equal to zero, then the sum to infinity must be divergent. And we must keep in mind, this is, first of all, this is something called the divergent test, and this is something where if you get a question where it says, is this sequence divergent, or is the sum of the sequence divergent or convergent, what you can do is apply this test. If the limit of the final term is not zero, then you know for sure it's divergent. But keep in mind that if it is zero, if the final term is equal to zero, that does not mean that the sum is convergent. Okay, it does not mean. If the final term is equal to zero, it could be the sum could be divergent or the sum could be convergent, and we wouldn't know. So that's a really big important thing to keep in mind. And this thing's not stating that, right? This one's not saying that. It says that if the sum is convergent, and that's dependent on the sum being convergent, then the limit of the sequence must be equal to zero. But if the limit of the sequence is zero, that doesn't guarantee the sum being convergent. Okay, so let's look at a few examples, and then this will lead up to the next theorem as well. So let's look at the sequence 1 over n. So let's look at the limit to infinity of that. That's going to be equal to 1 over infinity, which is equal to 0. And so the final term is 0, and therefore we can't apply the divergent test. We don't know whether the sum of the sequence is going to be divergent or convergent. So what we're going to do is we can compare the sum to infinity of 1 over n to the integral, the improper integral of 1 to infinity of 1 over x dx. And what we recall is, if you remember this form, 1 over x to the n, if n is less than or, if n is less than or equal to 1, that is divergent. And if n is more than 1, then the integral is convergent. And so therefore, if we see that this is 1 over n to the 1, then we can reason that the sum to infinity of this would be divergent as well, because if n is less than or equal to 1, it's divergent. If it's more than 1, it's convergent. Keep in mind that the answers from doing this integral and comparing it to an integral will not give you the same answer as the sum. It just won't. But it can give you the relationship. We'll look at that later. Another example here is where we have the sequence 1 over n squared. And so here, again, the limit goes to 0, and so we don't know if this is divergent or convergent. We can't apply the divergent test. So we, again, look at the idea of the integral from 1 to infinity of 1 over x. And in this case, the n is to the power of 2, and because it's larger than 1, therefore it's convergent. And so therefore the sum to infinity of this is also convergent. So, again, the takeaway, just to reiterate this, because apparently it's a very common mistake, is that when the limit of the sequence, the final term of the sequence at infinity, is equal to 0, we do not know whether the series will converge or not. So that's why you have to use alternate ways. And a quick illustration of why we can draw this comparison. Again, let me say again that the area under this graph is not equal to this sum, but the relationship is similar. The relationship is identical. So we can just do this really quick. These rectangular bars represent that sequence right there, which is 1 over n. So 1 over 1, 1 over 2, 1 over 3, 1 over 4, all the way till 1 over k. And this is the function 1 over x. And you can see how the area under this graph, area under 1 over x, is always going to be smaller than the area under these rectangles, right? And so if 1 over x is divergent, as we know from our theorem before, then these rectangles, the area of these rectangles, must be divergent as well because they're larger than the graph. So that's an idea. And I'm going to skip this one. This one's for 1 over x squared. But basically, I want to reach this theorem here, that is called the integral test. So if you had, suppose f is a continuous function and it's larger than 0 and it's decreasing on the domain 1 to infinity, then the sum from 1 to infinity of fn, if that is convergent, then the integral from 1 to infinity of fx also converges. So basically, whatever function you got for your sequence, if that is a continuous function and decreasing on 1 to infinity, what you can do is you can do an integral of that function. And if that function is convergent, then the series would be convergent as well. So again, if the integral of that function is convergent, then the series is convergent. If the integral of that function is divergent, then the series of that function is divergent. But keep in mind, if it's convergent and you get a value from fx, right? You do this and you find that the limit is equal to 2. That does not mean the series is equal to 2. It does not give the same answers. It just gives the relationship. Okay, so let's look through a few examples we did. So this is a series of a sequence with the formula 1 over the square root of 2n plus 1, and therefore we want to look whether it diverges or converges. So, and that's the only answer we have to answer. And so let's use the integral test and do an integral of this function. I did the integral here. This is the derivative, I think that's what it's called. But anyways, this is what the result of the integral is. And when you plug in t goes to infinity, what you get is an infinity. So since the integral, this improper integral, is divergent, therefore the series with the same function will also be divergent. And so this is divergent. The next example here, we have 1 over n squared plus 1. This is a bit more complicated. I just copied down the answer. But if you do the integration, and I believe you do it with trig substitution, what you end up with is this situation right here. And if you put t as infinity into here, what you get here is that t is equal to if t is equal to infinity, arctan of infinity, we see here arctan goes to infinity when it's pi over 2, so that's pi over 2 minus pi over 4. So yeah, this is convergent, but remember this answer here, pi over 2 minus pi over 4, which is 2 pi over 4 minus pi over 4, so it's pi over 4, the answer is pi over 4. This area given by this integral is not the same answer as the series. If we were to calculate the series with the there's really no way to calculate this actually, because we haven't done any equations for it, because the equations we've learned only works for geometric series. But anyways, the answer here is not the same as the answer you get here. This is just shows you the relationship. It's convergent, therefore this is convergent. So this is our answer. And this, so that's a really important test that we can use. And a kind of series or a sequence that we're going to be really kind of using a lot is something called a p series. And it's just in this form where it's a series, it's a sum of the function 1 over n to the p. So 1 over 1 to the p, 1 over 2 to the p, 1 over 3 to the p. If you think p is squared, it's 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared. Yeah. And it's a tricky kind of circumstance because it's not geometric. Geometric would be 1 over 2 all to the power of 2 all to the power of 3 all to the power of 4. But this here, the power is fixed and it's the denominator that's increasing, and it's a whole new form by itself. And so it's a distinct form by itself, and that's why we have a specific name for it. It's called a p-series. And again, if you do the integral test for simple kind of p-series, you'll find that it's the same thing as that improper integral theorem that we've used before, but we're going to be doing a bit more difficult kind of forms of this too. And and I want to bring to your attention that there is again another test, and it's called the direct comparison test. And this is similar to comparing improper integrals or the squeeze theorem if you see my previous videos. Basically, if you have a sequence, let's say you had a sequence A and B, right? And the sequence A is smaller than sequence B, and they're both larger than 0. But sequence A is smaller than sequence B. So if sequence B is convergent, if sequence B goes down, then sequence A must also go down. If you think of it like sequence B goes like this, and we know sequence A also goes down, is lower than sequence B always, then sequence A will be convergent as well. So if the larger one is convergent, the smaller one's also convergent. They squeeze down. If A is divergent, the smaller one is divergent, then the larger one must also divergent, must also diverge. So again, it's similar to the idea from improper integrals or the squeeze theorem. And I want to bring you guys' attention to this kind of condition, is that it only matters for really large n's. So later on in one of the examples, we'll bring up an example where this condition isn't true until like a specific a specific n. But that doesn't matter, because what matters is when n is really large and you're getting really big numbers, or like, yeah, you're getting really big numbers, and that's when this really matters, to be able to do the squeeze, to be able to compare. And so even if the condition fails for maybe like the first 10 n's, as long as the later ones are true, then it's fine. It's not same as the improper integrals one that requires it to be true for all n's. This one is just for really large n's. So let's look at a few examples, and we'll walk through the kind of thought process to go through these questions as well, so we know how to do them on the test. So if you had the series of the function n over n cubed plus 5, and we want to find if it's divergent or convergent. So the first thing we should always go for is the divergence test, because it's really simple. So let's find the limit of this to infinity. So you have n over n cubed plus 5. If you do some transformations to it, right, if you have n over n cubed plus 5 and you multiply this by 1, but a special form of 1, which is 1 over n cubed over 1 over n cubed, what you get would be 1 over n squared, because n times 1 over n cubed would be 1 over n squared, and it will be 1 plus 5 over n. Yes, 5 over n squared. And if you let n equals infinity, what you have is 1 over infinity squared over 1 plus 5 over infinity squared. So you have 0 here, 0 here. It will be 0 over 1, and therefore it's going to be equal to 0. So if the limit is equal to 0, then the divergence test has no effect. You can't tell if it's convergent or divergent, the series. So now we're going to look for different series to compare. So there's many kind of types of series to compare it to. So we have a constant series where the sequence is just the same number over, and we can compare it to that. We have geometric sequences where there's a common factor, a common ratio, and then we have p-series. And since this function itself is already a p-series, then we should compare it to a p-series. So the first step to kind of finding a series that we can compare it to is we kind of want to look at what happens when n gets really big. So when n gets really big, what you have is a big number here, a big number here, and a insignificant number here. So what you end up with is honestly n over n cubed plus 5 really just becomes n over n cubed for really big numbers. And so what's n over n cubed? That's going to be 1 over n squared. And what we're going to try to do is we're going to try to kind of mess around until we can find 1 over n squared in a way that kind of we can compare it to. So one of the first thoughts we should have is, hey, what's the simpler part of this fraction? N cubed plus 5. Okay, and a great way to get n cubed plus 5 to compare something is just say n cubed is I believe, yeah, let's try doing something like n cubed is smaller than n cubed plus 5, for example, and then we can do some manipulation from there, is kind of the first thought I would have. And so what we have is, okay, let's do this. So n cubed is smaller than n cubed plus 5, that's for sure. We divide by 1n, that gives you kind of the inverse of what we want, right? We want 1 over n squared, and we want n over n cubed plus 5. But what we have now is n squared and n cubed plus 5 over n. So what you do is you take the reciprocal of this. And when you have the reciprocal, you have exactly what you want. 1 over n squared, which we know the properties because we can do the integral test of this from 0 to infinity of 1 over x squared, and we know if it's larger than 1, it's convergent. And then we also have n cubed over n cubed plus 5, n over n cubed plus 5, which is exactly the function that we're looking for. But notice how the sign changed. I just want you to think that if you had a number like 0, if you had 1 is less than 2, and then you take 1 over 1 and 1 over 2, what you have now is 1 and 0.5. And so if you divide by a larger number, the result is smaller, and so therefore the sign should change. So that's the kind of logic here. And so if you see that we have 1 over n squared is larger than n over n cubed plus 5, we can rearrange it into that order where it's 0, and is then the next thing is the second largest, and the second largest would be n over n cubed plus 5, and then the third largest, the largest one, would be 1 over n squared. And we know that 1 over n squared is convergent through the integral test, and so if the larger one is convergent, the smaller one is convergent too, so therefore it is convergent. Therefore, n over n cubed plus 5 is convergent. So finally, we have one final example here to kind of look through. So we have the sequence of ln of n over n. And we're going to look at whether it's divergent or convergent. So again, let's try the divergence test. If we do lim to infinity, we have ln of n over n. That's infinity over infinity. Again, remember another theorem that we did in the last video is that sequences are just functions. You can treat every term in a sequence as just a function. So if you have infinity over infinity, you can do L'Hopital's just like any other function. So we do L'Hopital's. This gets us 1 over n over 1. If you do n to infinity, that's 0 over 1, which is equal to 0. And therefore, the divergence test gives us nothing. It doesn't tell us whether the sum to infinity is divergent or convergent. So therefore, we're going to have to do it through some other ways. So let's first do a comparison test. And the best way that we can look at it is because if we know how, again, we always kind of want it in the form of 1 over x squared, 1 over x cubed. We really like this because we can do the improper integral from 0 to, not 0 to infinity, to 1 of 1 to infinity. Did I make that mistake before? I mean 1 to infinity, guys. But yeah. From 1 to infinity, the improper integral of this. And we know whether these are convergent or not, because do we know if this is 1 or if it's less than 1, then it's divergent. If we know it's larger than 1, so 1.1 upwards, then it's convergent. So we kind of want to do something here where we want to be able to take 1 over something. Okay, so then let's start with 1, right? So we have ln n is larger than 1. Now that's not strictly true. First of all, this is a logical way to start out. This is really good. But think about whether this is actually true or not, right? Imagine if n equals 1, which is the first term, you have ln of 1 is actually 0. So with this, we're saying that 0 is larger than 1. But again, remember what I said before. What matters is for really large numbers. So when this crosses e or whatever, like ln of e, and then it starts going higher and higher, that's when this really all matters, because yes, it could be larger just at that first step, but then as it goes here, that's what matters, right? The largest n is what matters. So we can keep on going with this postulate and we can treat it as if it's true. And so now we divide everything by n. We have ln of n over n, exactly what we want, is larger than 1 over n. And so again, let's rearrange this into the form that we know. 0 is smaller than 1 over n, which is then smaller than ln of n over n. And therefore, we know that 1 over n, same thing as 1 over x, we can do the integral test from 1 to infinity of this. And this gives us divergent, because again, if p is equal, p is less than or equal to 1, then it's divergent. So this is divergent, and therefore the larger one, the smaller one's divergent. So the larger one is also divergent. We can also do the integral test with this, and it's actually quite a simple integration. So you just use u substitution, you end up with u du. It's really simple, and basically you end up with this ln squared of n, and if you plug t in, it's ln of infinity squared, and so again it's infinity. So it's divergent both by integral test and by the comparison test. But yeah, that's it. So that's what we did today. Oh, and there's one final theorem, and this one's really simple. So if you have a sum, right, if you had 1 plus 2 plus 3 plus 4, that's the sequence, and you're plussing these together, right? You know for sure this is divergent because it's just going to increase to infinity. So if you start taking the sum from here instead, if you start taking from 4, 5, and 6, and 7, so the sum starting from 1, that's divergent. The sum starting from 4 is also divergent. That's kind of like obvious, but it's just a theorem that you can remember. And if something's like 1 plus 0.9 plus 0.8, and it goes down to like 0 point something and 0 and ends up like really low, and turns into 0 and then turns out to be convergent as well. If you start from 0.8 instead of 1, it's also convergent. So basically, the index does not matter. But yeah, that's it for today's video. Thank you guys for watching, and see you guys next time.